Look at Q4. Q4 is vertical right now, right? So it was used for complex calculations. But if you move this one spot like this, Q3 can perform complex calculations. Hi everyone, nice to see you. This is Era, sick from DeepSeek. Last week, during the Seollal holiday, while I was diligently rowing my deep-sea boat, a groundbreaking paper was published. This is precisely the approach that IonQ, a quantum computing company, is advocating for. There has been a groundbreaking technology announced regarding ion trap-based quantum computing. Originally, this ion trap method was noted for being less error-prone and more stable compared to the superconducting methods used by IBM, Rigetti, and Google. Nevertheless, now, Seoul National University has published a paper on arXiv that addresses and enhances the challenges faced by the ion trap method. So, how does this method overcome the limitations of the existing ion trap technology? This allows companies like IonQ to make further progress. Let's analyze how these issues were solved and how the technology will evolve based on the research paper. Let's get started. I've often explained quantum computing and made various content, right? I've talked a lot about IonQ's ion trap method, the superconducting method, and Google's Willow approach. Honestly, it's pretty complex, right? Isn't variance typically handled by GPRs? So, many of you might be thinking this way. And for those who are seeing this for the first time today, let me explain it in various ways. All computers are represented by bits, 0 and 1, right? Everything is represented by numbers. A quantum computer possesses the extraordinary capability to represent multiple states simultaneously using qubits. So, as I always mention, it's quite similar to Doctor Strange from the Avengers, where he lives multiple lives simultaneously in different universes, like in a multiverse. However, for quantum computers to rapidly and efficiently process everything, they need to be in a state where all operations are happening concurrently. To enable parallel processing, we frequently talk about concepts like superposition and entanglement. It's crucial to sustain this specific entangled state continuously. For a more detailed explanation, you can watch my other videos. It's crucial to maintain a state known as entanglement consistently. For more details, check out other videos where I've explained this extensively. To keep qubits stable without interference, companies like IBM, Google, and Rigetti use superconducting methods. IonQ, on the other hand, uses ion trap technology to maintain qubit states. Each method has its pros and cons. So this quantum computer, unlike a regular computer that just needs a battery or a power cord to run, is quite different. In order to perform transformative calculations, it is crucial to maintain the state of a qubit with great precision. These qubits are incredibly sensitive, though. Even the slightest change in conditions, like a minor temperature shift or a tiny movement of the ions, can easily cause errors to occur. To address these issues, a method known as quantum error correction is used. Previously, I talked about Google's Willow chip, which utilizes a superconducting approach to manage these errors. This method effectively organizes quantum error correction into a two-dimensional lattice structure, allowing for the capture of errors as the number of qubits increases. It's crucial to differentiate that a high incidence of errors can lead to failed computations. Nevertheless, even when errors do arise, quantum error correction can be implemented to rectify them, thereby minimizing the overall error rate. IonQ has skillfully utilized this method to extend the coherence time significantly, which refers to the duration for which the system remains stable. I just mentioned fixing errors, correcting errors, you know. Originally, for classical computers, let's say it's 10. In classical computers, error correction is a technique. If the original number is 101 and an error occurs, you might not know what the error is. So how do you fix it? By sending a bit more information. For example, if we send the sum of the first and second numbers, and then the sum of the second and third numbers, we can check for errors. Even if the third number, originally 1, is read as 0 by mistake, we can still verify it. If the sum of the first two numbers is 1, it's fine. But if the sum of the second and third numbers doesn't match, we know something is wrong. In this way, classical computers often use error correction. In server DRAM or LTE-5G communications, errors often occur when signals are modulated and demodulated and decoded, so error correction plays a crucial role here. Quantum error correction, which deals with fixing errors in quantum bits, or qubits, when they are in a quantum state, is something you should understand at a basic level. So what exactly has changed when we apply this method? Using IonQ's ion trap approach for quantum error correction in quantum computers hasn't been easy. Essentially, each ion acts as a qubit, or quantum bit, and the computations are performed by moving these ions around, right? As we move each ion one by one, you know how our Pocari sweat ions behave, right? They don't seem to move exactly as we want with lasers, just like the Pocari sweat ions, don't you think? So, when we transfer qubits, numerous errors occur. Specifically, in the ion trap method, this qubit movement is highly prone to errors. To utilize our computational abilities, we must move them, which inevitably takes a considerable amount of time. Compared to traditional methods, the ion trap approach is naturally slower, due to the need to move these ions. Let's delve into why qubits needed to be moved in earlier methods. The ion trap technique involves qubits interacting with each other to perform calculations. They need to come into slight contact to execute the desired operations, which is how the computations are carried out. But these qubits, which are ions, are usually arranged in a straight line. So by using a laser to manipulate them, we need to bring the specific qubits we want together, say qubit 1 and qubit 5, to execute a quantum logic gate operation like the CNOT gate. However, since these qubits are physically apart, we need to move the ions to bring them closer. This process not only takes time, but also introduces noise errors. Errors can arise during calculations. Also, qubits need to be stored separately when not in use. Returning them to their original state takes time. Now, why do qubits become so sensitive when they move? As I mentioned, qubits are extremely delicate. Any disturbance can cause errors. In this ion trap method, an electric field is used to control and move them. If the control isn't precise, the ion can become unstable, leading to stress and potential errors. Additionally, it can easily be influenced by external factors. There could be air molecules or slight vibrations affecting it. The ion trap method is time-consuming because you cannot perform calculations while the ions are moving. This inability to calculate during movement extends the overall time required. However, this new research paper addresses these issues to a certain extent. Here is the paper, titled Quantum Phoenix, which was submitted on January 25th. They seem to be proud Korean graduate students and researchers. They proposed a new ion trap chip architecture. They suggested a new architecture that incorporates a fabricated quantum error correcting code, proudly bearing the name of Gwanak, Seoul National University. Several researchers from various affiliations contributed to this study, which spans over 20 pages. To summarize the key points from this lengthy paper. So, before we dive into the details, let me explain what they did. You know the errors I mentioned, right? The quantum errors. They created an architecture that corrects these quantum errors more effectively. It also addresses the challenges of the existing ion trap method. To be more specific, more errors occur as you move around. They found a way to minimize this movement. I optimized it, arranged everything well, and I'll show you the diagram later. And the error correction happens automatically like this. Now, I won't go into detail about the color codes and such mentioned in the paper. If you want to know more, I'll make separate content, but I doubt you'll be that interested. The problem with the traditional method is that when we perform calculations, there are both straightforward and intricate operations. We refer to the simpler ones as transversal gates and the more complex ones as non-transversal gates. These need to be executed simultaneously in the same space, which results in a mix of simple and complex calculations. So, essentially, there were many instances where they had to move these ions around. They lined up all the qubits in a row and performed calculations by shifting the necessary qubits to the side as needed. In this research paper, they tackled this by completely separating the simpler transversal part from the non-transversal part. Look here, this is the architecture diagram. It might not be clear, but you can see the brown dots. The ones that are greenish-blue are all for simple operations, as I mentioned earlier. They are for transversal gate operations and are arranged in a single line. Then do you see the vertical ones here? The blue ones. This blue part is configured vertically to set up non-transversal gates, which can handle more complex calculations. By arranging them horizontally and vertically, you can see that the vertical part has openings, allowing for different configurations. If you look at this diagram, you can see the vertical part with openings, which is designed for complex calculations. The horizontal arrangement is for simpler calculations. Here you can see the before and after of the movement. Now how does it move? Check out Q4. It's positioned vertically, right? Remember what I mentioned about the vertical ones earlier? We used it for complex calculations, but if we move it one step to the right, Q1, Q2, and Q3 all shift right. Now Q3 can handle the complex calculations. Previously, if Q1 and Q5 were needed, we had to fetch and move them manually. Now, the setup allows some calculations to be done vertically and others horizontally. They designed it to enable calculations through both horizontal and vertical movements. By structuring it this way, operations decrease from the start, so errors also reduce. This means less time is needed. We tested several algorithms. As you might know from previous videos, in quantum computing, you need specific software algorithms. These must maintain the entangled state well while performing operations. So here you can see things like the quantum Fourier transform. We tested famous algorithms like Grover's. So the red and purple lines are without quantum error correction. The others have it applied. On the horizontal axis, you see the qubit gate error probability. It should be raised to the 4th power within 10 trials. This is already at the order of 4. As you go further up the 4th order, without error correction, even a slight increase in horizontal axis probability drops the success rate. But do you see how the others gradually increase? By using quantum error correction, or QEC, we can significantly lower the error rate. Naturally, if the initial error rate is low, the success rate is much higher. Even with a 0.5% error rate, it rises to over 80%. Although there are variations depending on the algorithm, this has been implemented. Specifically, in the complex vertical sections I mentioned earlier, error correction is applied only to those parts. Meanwhile, the qubit transitions. Essentially, they apply error correction only to the parts where errors occur most frequently. So the ion trap method usually has few errors, but they found a way to reduce them even more. So, do you think IonQ will do this even better? Is this paper related to IonQ? So I looked it up and found a press release from Seoul National University. They signed a research agreement with IonQ for quantum talent and industry collaboration. At this point, we have Kim Jong-sang, the CTO of IonQ, who shared some insights. Maybe they use the ion trap method for international quantum cooperation? If anyone knows, please comment and let us know. Thanks. Ultimately, IonQ can carry out computations with fewer mistakes, making it more dependable. By fine-tuning these errors, the likelihood of achieving a stable, large-scale quantum computer has significantly increased. Especially since it reduces the movement of ions, there are parts where hardware efficiency can be increased. Given this, IonQ is currently considered a mid-range quantum computer, known as NISQ, due to some noise. However, if this method becomes more active, we might be able to scale up to a fully fledged, large-scale quantum computer. So I summarized it like this. Of course, this isn't a complete fix. We still haven't managed to fully eradicate errors, and the hardware setup can be quite complex. Expanding too many qubits still has challenges. Many issues need to be addressed in the future, but that's how I see it. We always make small improvements in technology. Our graduate students, professors, and researchers are all working incredibly hard. As a result, things like AI, which people said would never happen, are happening. Autonomous driving, which people said would never happen, is happening too. So there is this progress delta. Because this delta keeps existing, even just verifying these things contributes to technological advancement. Following these trends can be quite exciting. I truly admire the dedication of the researchers involved. I have put together a brief summary to share this information with you all. Anti-Engineering's Instagram now has 3,000 followers. Here are some fun things like wireless shower jokes. They call it a Bluetooth showerhead, and the water comes out via Bluetooth. There are also interesting things we cannot cover on YouTube. Not just fun stuff, but also simple news clips you can easily watch. So please show a lot of interest. This has been Error.